Hi, my name is Bingqing Zhang, and I'm honored to present our work, Understanding Interactions for Smart Wheelchair Navigation in Crowd. This work is a part of Crowdbot project and is collaborated with Dr. Giulia Barbareschi, Roxana Ramirez Herrera, Dr. Tom Carlson, and Dr. Catherine Holloway. Shared control wheelchairs can help users to navigate through crowds by enabling the person to drive the wheelchair while receiving support in avoiding pedestrians. To date, research into shared control has largely overlooked the perspective of wheelchair users. This paper answers an important research question. What do power wheelchair users need to be able to use a shared control wheelchair in a crowded environment? And how can we design new interactive systems that ensure safe and empowering navigation experiences? To address this question, we conducted two studies. Study 1 explores the requirement for smart shared control wheelchair navigation in crowds. To achieve this, we conducted a series of semi-structured interviews with 15 powered wheelchair users. Interestingly, although most wheelchair users identified crowds as one of the scenarios where frequent collisions happened, they thought that the problem was largely associated with pedestrians' lack of awareness and understanding of power wheelchairs, rather than the control of the wheelchair itself. In addition, participants often find that power wheelchairs did not provide any helpful feedback about the surrounding environment. As a result, we summarize the need for communication as internal, the one between wheelchair and the user, and external, the one between the wheelchair user unit and the pedestrians. In general, collision avoidance is appreciated, but users express a need for balancing safety, autonomy, and social aspect. For example, the level of autonomy should be based on the scenario and the user's capability. This further led to some interesting reflections amongst the participants about negotiating shared control from an ethical point of view. Participants also raised concern about the system overriding the user's command. By examining users' point of view in Study 1, we highlighted the need for smart wheelchairs to have a clear and effective internal and external communication system. To further explore this aspect and identify potential solutions for successful user-wheelchair pedestrian interaction, we conducted a second design-focused study. It was conducted virtually by Teams, where 6 adult power wheelchair users and 2 designers have joined. Participants were asked to design the communication system for smart wheelchair, which would allow our character Anne to navigate in 2 typical but inherently different crowd scenarios, crossing a busy street and reaching a help desk in a crowded hospital. Results indicated that the type of internal information needed includes what the wheelchair has perceived, what the wheelchair has decided, and the alignment or deviation between the user and the wheelchair. Externally, the smart wheelchair and the user should communicate wheelchair-related information to the surrounding pedestrians. In terms of interaction modality, there is a clear preference towards a combined audio and visual feedback system to manage internal and external communication in the street scenario, while inclination towards visual and haptic feedback modalities rather than the auditory ones has been observed in the hospital scenario. For the location, participants expressed a preference for interfaces connected to internal communication system to be positioned on the wheelchair itself or to be embedded in a wearable device like a wristband or a watch that could be worn by the user. As for the external one, no specific location preference was discussed. However, providing auditory or haptic feedback directly to pedestrians could be perceived as a weird invasion of one's personal space. During the design workshop, participants worked together with the designers to create their desired interactions for the 2 crowd scenario. These 2 figures are sample design output from the crowded street scenario. On the left-hand side, traffic color-coded projection is used to indicate the wheelchair speed. On the right-hand side, wheelchair's trajectory and its deviation from the user's intention is indicated through parking trajectory-alike system, either being projected or pop up in an add-on screen. Short and long audio signals are used for warnings. For the crowded hospital scenario, designs are slightly different. Expected paths and locations of obstacles are projected in the left one. A switch is used to turn this function on and off. The right one shows that when the wheelchair is getting close to pedestrians, the user receives warnings through wearable haptic device. Based on the result from our studies and the reflections, We elaborated a series of design implications that we believe would be crucial to the development of future smart wheelchairs. First of all, we noticed additional requirements related to the need to include elements of empathy, embodiment, and social acceptance in smart wheelchair interaction design. Participants stated that they would consider a smart wheelchair as an extension of their body, akin to what has been previously reported for different types of assistive technology. As such, the way in which the smart wheelchair provides feedback to the user needs to feel appropriate, matching one's expectation for embodiment, which might be different across individuals. Moreover, when it comes to the external communication, the way in which the wheelchair enables interactions between the user and surrounding pedestrians should incorporate considerations around social acceptability and empathetic communication. Situation awareness and adaptability are possibly the two most important key features for smart wheelchair interaction systems that we have identified across the two studies. In order to be effective in a variety of environments, the control and interaction system need to have a great degree of flexibility. Moreover, smart wheelchairs also need to be able to respond to shifting capability and the changing preference of users, adapting not only their mode of interaction, but also the degree of assistance provided to the individuals. Previous studies have shown that being bombarded with excessive information in a short space of time can lead to overload, which negatively affects an individual's performance. Similarly, in our study, participants expressed the preference toward having only selected information to be provided at the appropriate time so as not to overload the user as well as the surrounding pedestrians. So in the end, we would like to wrap up by highlighting our contributions as: first, we presented an understanding of requirements and challenges for smart wheelchair use in crowd. Secondly, we present the conceptualization of an interactions interface for smart wheelchairs, which helps to manage interactions between user, wheelchair, and pedestrians across different crowd scenarios. Third, reflections on implications of findings highlighting the need to create empathetic communication between wheelchairs and other pedestrians, promote situational awareness to ensure adaptability, and manage information overload during navigation in crowded environments. That's all for our presentation. Thank you.